In this video, we're going to look at use implicit differentiation to look at the tangent lines to the graph x equals y to the fifth minus 5y cubed plus 4y. Now, first off, this thing cannot be written as an explicit function of x because this can't be solved for y. And if we look at the graph, we can see it clearly does not pass the vertical line test in multiple points. So what we're going to use is implicit differentiation to determine a formula for the derivative. So let's go ahead and do that. And so what we're going to do is we're going to differentiate both sides with respect to x. So we're going to do d dx of x and d dx of y to the fifth minus 5y cubed plus 4y. Now remember, we're thinking of y as some function of x. Alright? It's an implicitly defined function of x. So what that means is anytime we take a derivative of a y term, it's going to be a chain rule. Now when we do the derivative of x with respect to x, that's easy. It's just 1. But now as we go through this piece by piece, we have to consider each as a chain rule. So when we do the derivative of y to the fifth, it's going to be 5y to the fourth. But then that's going to get multiplied by the derivative of the inside, which is y, which is dy dx. Minus, now we're going to do it with this term. It's true that from our power rule, derivative of 5y cubed is 15y to the second. But because y is an implicit function of x, we have to multiply by the derivative of the inside, which is dy dx. Now we can kind of generalize this. Anytime we take the derivative of a y term, we're multiplying by dy dx. So the derivative of 4y is just 4, and then the derivative of y is dy dx. So there's going to be our derivative, and what we want to do is have, if possible, have an explicit formula for dy dx. Now this one's not too bad because notice on the right hand side every term has a dy dx in it, so I'm going to factor that out. So dy dx times 5y to the fourth minus 15y squared plus 4. And finally I'm going to swap this over here. My dy dx explicitly solved for dy dx, which is not always going to be possible, is 1 over 5y to the fourth minus 15y squared plus 4. Alright, this one only involves y, but it's very possible your derivative will involve both x and y. Now part C, what we're going to do next is let's find the tangent line at the point, so let's find the tangent line at the point 0, 1. Remember two things we need for a tangent line. We need the slope and a point that it goes through. We got the point. The slope m is going to be our dy dx at the point 0y. So you might write that thusly. So that means we're plugging 1 in for y. So we have 1 over, plugging 1 in for y is just going to make this 5 minus 15 plus 4. So our slope of our tangent line is going to be negative 1/6. What that tells us is our line is going to be y equals negative 1/6 times x minus 0 plus 1, or negative 1/6 x plus 1. Now we went ahead and did our tangent line at the point 0, 1, so let's see where that is on our graph. So right there is our point. So this tangent line we just found is going to look roughly like this, and we can see that negative slope in there as we draw our tangent line. Now the last thing we're going to do is find all the places where m is undefined. Okay, and there's going to be several. It means we have a vertical tangent. So if we look at our graph, let's kind of get an idea of where we're going to have vertical tangents. Well, it's kind of the equivalent of a horizontal tangent. So all these turning points we would expect to have a vertical tangent and thus the slope be undefined. So what we're seeing from the graph is 4 places where the slope's undefined. Well, how we would find that algebraically, m is going to be undefined any place the derivative has a 0 in the denominator. So that's what we need to calculate. And it's not an arbitrary calculation, but it's going to happen wherever 5y to the 4th minus 15y squared plus 4 equals 0. So that's what needs to be solved. Some ways of solving this is going to be using a graphing calculator or using a computer algebra system like Maple or GeoGebra. If you do that, you're going to get the y values plus and minus 0.5439 and plus and minus, this is for the y's, positive and negative, I wrote that twice for some reason, 1.644. Now, finding the x's that are associated with that, you're going to plug these into the original function because we got the y values and to get the x's so we can see what points those are. So that you know, so that you have the solutions in case you want to check, the points are going to be 1.419, comma 0.5439. We're going to have another point at negative 1.419, negative 0.549. We're going to have another one at negative 3.631, comma 1.644. And finally, the last one's going to be at 3.631, comma negative 1.644. Again, this would just be a matter of taking this equation here, plugging into a graphing calculator or a computer algebra system, finding the zeros, and taking the values you found there and plugging them into the original function. Now let's see how those match up with what we have on our graph. So it may be hard to get all of this on here at the same time. So look at where we have our vertical tangents plotted on our graph. And here's our points. So about 1.5 and a half right there. So that would correspond to that point. Negative 1.5 roughly, negative and a half right there. So those are nice and symmetric. And finally, negative 3.6 and 1.6. We see that one. And positive 3.6 and negative 1.6. So notice we have a function with odd symmetry as well. So that's how we can find places where there's a vertical tangent. We're looking for where the slope is undefined.